Hello, this is Mr. Gilmore with the 1.3 Polygons lesson. We have seen in the first several lessons some of the building blocks that we're going to be using in our geometrical system, such as points and lines. We've also looked at segments and rays. We also looked at angles. Well, now what we're going to do is use those segments. We're going to form new figures today known as polygons. So what is a polygon? Well, the definition of a polygon is actually pretty extensive. There are three things that we have to list out for a figure to be a polygon. Let's take a look at this definition together. The first thing is a polygon is composed of line segments. That's the very first criteria that a polygon must have. Let's look at the next sentence. Each intersects, this is actually talking about the line segments, each line segment intersects precisely two others, one at one of its endpoints and the other at the other. That's the second part. Second criteria that a polygon have. So we have these line segments composed of only line segments, and they're intersecting precisely two others. Last but not least, adjacent segments are not collinear. Adjacent means touching, right? They're shared. So adjacent segments are non-collinear. An example of this would be like, let's say I have a diagram like this. Like here's a line segment here, and then I have another line segment here. And so these are adjacent line segments, but if they are collinear, that does not count then as a side of a polygon, okay? So just be careful. That is a no-no. It goes into the definition of polygons. Now we call the sides of a polygon, or sorry, we call the segments that make up the polygon the sides, and then we call those intersection points of the sides. We call those a vertex. For the entire polygon, since we have plural of the word vertex, it's of the word vertices. So we will see that we have vertices of the polygon that we'll be actually looking at as well. Here's just a quick diagram of a polygon. If you notice that this is a five-sided polygon, notice it's composed of solely line segments. We've pointing at the side there, which is a line segment. We have the vertex, which is that intersection. As we go along with the definition, we see that each side intersects precisely two others, right? One at one endpoint, and then the other at the other. Okay, and no two line segments that are adjacent are collinear. So we pass the definition. Check. We've got all three of the criteria met for the definition of the polygon. Now, we're going to look at different types of subsets of polygons. In order to do that, we have to define a new word called a diagonal. So since we have line segments, or what I would call adjacent vertices, right? These are the vertices that are next to each other. We can have actually a pair of non-adjacent vertices within a polygon. And so if we were to connect a segment from one vertex to another non-adjacent vertex, we would call that segment a diagonal. Now we're going to use this diagonal then to define two separate subsets of polygons. We have what we call concave polygons and convex polygons. A convex polygon is where we find all the diagonals, and I really mean all the diagonals, of any given polygon to be on the inside or lie on the interior of the polygon. A concave polygon, then, is where you find at least one diagonal to be on the outside or to pass on the outside of, or the exterior of the polygon. Let's take a look at an illustration of a diagonal first. So the diagonal here we see is connecting two non-adjacent vertices. If I were to pick this vertex here and say what were its adjacent vertices, these two would be the adjacent vertices, right? Those are the ones that are next to it. So I could pick any non-adjacent vertice, right? So any non-adjacent vertice to this given vertice would be these two. So if I connect those, I can actually connect another diagonal here, and I find that yes, this diagonal passes on the interior. Now to check it, what I could then think of is, what about all the other diagonals? What if I were to pick a different point? Would they also pass all through the interior? And they would. So let's go back to that diagram. If I were to actually connect all of the diagonals, I should say distinct diagonals inside of that diagram, notice all diagonals pass through the interior, which means we've got ourselves a convex. Down here in our second example, we have our concave. Concave, we do have a diagonal here, okay, that's connecting those two adjacent or non-adjacent points. But notice what happens here when I connect these two non-adjacent points. These two non-adjacent points cause the diagonal to pass on the exterior, which then means we define this polygon to be concave. And you'll see that we'll work with both convex and concave polygons throughout the year. To name a polygon is very simple. Since we have vertices, which are these points of intersection, and we know how to name points with capital letters, let's use the vertices to help name the polygon. So how we do this is we pick a vertice to start with. So any one of the vertices of our set of the polygon given, we just pick one of the vertices, we stick with that vertex. Then we pick a direction. That direction is we're going to be traveling since either clockwise or counterclockwise around the polygon. And every time we interact with a new vertex, we add the name of that vertex to the name of our polygon. Let's take a look at an example. So down in this diagram here, we actually have a four-sided polygon. This four-sided polygon has 4 vertices, which means I'm going to have to use 4 letters or the 4 vertices to name the polygon. The easiest way, or remember how we name a polygon, it's the easiest way is you just pick a vertex, and then you travel in a direction, and you stick with that direction that you've picked. So one name we can call this polygon is polygon WXY, and that's a typo, that should say Z, WXYZ. So what I've done is I've chosen W, oops, let me fix that. I've picked W as the starting vertex, and then I chose a direction. Let's head toward X first. Then I continue that direction that I've chosen, and I travel all the way around my polygon until I've actually named every single one of the vertices. So WXYZ, that is an appropriate name for my polygon. Could I have gone the other direction? If I start with W? Yes. If I started with W, could I have gone to Z? Yes. And then I could have gone to Z to Y, and then Y to X. Notice that I'm traveling only along the sides of the polygon. So because there is an invalid name here, actually several invalid names that I could name this polygon. Notice if I were to start here at X, I cannot go from X to Z, right? What have I really traveled along? I traveled along the diagonal, right? There's that diagonal that exists there. So you never want to travel along diagonals when naming polygons. You may only travel along the sides. And so if I were to start here at X, okay, appropriate name that I could use from X is I could either travel toward Y or I could travel towards Z. Let's say, or sorry, W. Let me travel towards Y. So I go X, Y, Z, W, that's a name for it. Or I can go back and I can do X, W, Z, Y. There's an appropriate name for my polygon. So if it has 4 sides, you know you're going to have 4 letters in the name. If it has 5 sides, you know you're going to have 5 letters in the name. All right, so that's the appropriate way of naming the polygon. Well, the worksheet holds a little bit more information about what polygons hold, so make sure you're reading through the 1.3 worksheet. If you do have any questions on that, please make sure you contact me, either email me, find some other way of contacting me. But with that, that's all there is to today's lesson, so be good and do good.